Thank you for being with us, and please go ahead, and then we can have a little chat.
Good. Okay. Thank you so much. Well, first of all, thank you for inviting me, and I'm sorry that I can't be with you in person, but I hear it's been a good conference, and I hope that you're still not too tired to listen to one more talk. So I'm going to start by sharing my screen. Good?
Yeah. Still not in presentation.
Yeah.
There you go. Let's see.
Okay, that should be good,
Yeah.
yes?
Perfect.
Good. Okay. Well, I thought I would start today by talking a little bit about why I wrote this book. Why did we need a book about trust in science? The first reason had to do with public lectures that I was giving in the United States and elsewhere. So after my book, Merchants of Doubt, came out, I was invited to give many lectures in which I often explained the history of climate science to help people understand how scientists concluded that the climate was changing because of human activities. And often when I would give these talks, someone would stand up and say, well, that's all very well and good, but why should we trust the science? And the more I got that question from people, the more I began to think, well, this is a question that many people have, and it deserves a legitimate answer. It's not enough simply to say, trust us, we're the experts. I think our audiences deserve an explanation for the question, an explanation for why science deserves our trust, if indeed it does. A second reason has to do with the problem of uncertainty. An awful lot of climate change denial and also rejection of other sciences focuses on this uncertainty. Climate change deniers often imply that because the science is uncertain, therefore we should ignore it, or therefore we don't need to act. Well, it is true, science is uncertain. Science is a process of learning and discovery, and that means that we will learn new things that may make us rethink the old things. And there's intrinsic uncertainty in all science because we never have absolute access to the natural world. So no matter what we do, we can never say that something is proven in an absolute sense. In addition, there was a third reason, and that had to do with the deliberate generation of mistrust. So in Merchants of Doubt, Eric Conway and I showed that the tobacco and fossil fuel industries have worked deliberately, consciously, knowingly to create public mistrust in science that showed the damaging effects of their product. So if we are going to fight back against the deliberate fomenting of mistrust, then we have to give an explanation for why that mistrust is misplaced. And then another reason. So as many of you know, here in the United States, until quite recently, we had a president and a vice president who denied major facets of scientific findings. And of course, this is not only in the United States. Mr. Bolsonaro in Brazil and other scientific leaders around the world have questioned the scientific evidence regarding climate change. And Mike Pence, the Vice President of the United States, has questioned the theory of evolution and the harms of tobacco use. So this is climate change and science distrust at the very highest levels of American politics. And so for all these reasons, and probably some others, it seemed important to take this challenge seriously and to try to answer this question. And then, of course, COVID-19 hit. As many of us have seen over the last 2 years, there's been tremendous resistance to the scientific evidence on the value of masking. Here in the United States, widespread rejection of vaccination. So here we are more than a year after safe and effective vaccines have been widely available and free of charge. 35% of Americans are still unvaccinated. And that's a high enough number as to prevent herd immunity. According to a recent study in The Lancet, more than 40% of the deaths that have occurred in the United States could have been prevented if we had followed public health guidelines more strictly and more quickly, and if people had embraced vaccination broadly. As you all know, more than 1 million people have died in the United States. That means something like 400,000 deaths could have been prevented if we had trusted and heeded the science. So what we see in the COVID-19 story is that this is not just an academic issue. We live in a moment when trust in science has literally become a matter of life and death. And then there's one more reason. In response to attacks on science, some famous and leading scientists have said a lot of things about science that really can't be defended. Like the famous astronomer Neil deGrasse Tyson has been going around saying, well, whether or not you like it, science is true. But science is an enterprise. Science is a host of different activities. To say that science is true would be like saying marriage is true or universities are true. I mean, science is a lot of different things. Sometimes our claims are true, but to say that science is true makes no sense. So let's talk a bit first about scientific uncertainty. When I think about scientific uncertainty, I often start with Pascal's wager. Pascal, as many of you know, was an important mathematician and philosopher who wanted to answer the question, does God exist? He posed what today we would think of as the problem of type 1 versus type 2 errors. What are the relative risks of believing in God if God does not exist versus believing if God does exist? If you frame the question this way, you realize that very quickly it's much safer to believe in God. Because if you do believe and it turns out there is no God, well, not much harm is done. But if you don't believe and there is a God, then you will burn in hell forever. So Pascal concluded that it is definitely better to believe. The risks of believing are much less than the risks of not. In other words, it's about the consequences of our belief. This is what philosophers call a consequentialist framework. And we can compare that to a nomological framework, which is to say a law-like framework, like the Ten Commandments. To put this in secular terms, you may not need it, but it's safer to hold on to the handrail. But this kind of conversation about God and religion may make it seem like I'm suggesting that science is a leap of faith. And of course, most scientists would reject that idea. But I think that often to ordinary people, science often does seem like a leap of faith. We're being asked to accept things that we don't really understand. Most people have very little idea how to judge whether scientific claims are true or not. And even many academics may not know how to judge claims in areas outside of our own expertise. Like Pascal, we assume that the risks of accepting most scientific claims are smaller than the risks of rejecting them. But should we? Should we trust science? And if so, why? What is the principled intellectual argument for confidence in scientific conclusions? The traditional answer to that question is to invoke the scientific method. That is to say, to suggest that scientific claims are true by virtue of the method that is used to arrive at them. Most commonly, this method is thought to be the hypothetico-deductive method, and you can find this in many textbooks, both in the United States and elsewhere. The idea that we develop a hypothesis, we deduce its consequences, and then we observe through experiment or observation in the natural world to see if those consequences are true. And if it is, then we conclude that our hypothesis is correct. Now, scientists do sometimes do this, and there are some very famous examples in the history of science. For example, the confirmation of the theory of general relativity by the bending of starlight. Einstein predicted that if his theory was true, or one of the consequences of his theory, was that if what we conventionally call gravity was really the bending of space-time, then we could see that bending of space-time through the bending of starlight as it passed by a massive object like the sun. This prediction was tested in 1918, and it was shown to be true. Now, sometimes philosophers call this the deductive nomological model, because in an ideal case, we aren't just trying to develop a hypothesis, we're searching out the universal laws of nature. But the basic idea is the same. And we can think of examples of this too, such as Einstein's famous law, E equals mc squared, or Newton's laws of motions, F equals ma, etc. The problem, however, with the hypothetico-deductive model is that as a logical claim, it doesn't actually work. And it doesn't work because of something called the fallacy of affirming the consequent. What that means in plain language is that just because a prediction comes true does not, in fact, logically mean that the hypothesis that led to it is true. So the most famous example of that in the history of science is the Ptolemaic system of astronomy. The Ptolemaic system that put Earth at the center of the universe made extremely accurate predictions of the motions of the planets and the timing of eclipses. Today, we would look back on this hypothesis and we would say that it was incorrect. We would say that we all know that the Earth is not the center of the universe, and yet this false theory made true predictions. There's a second problem as well, and it's the problem that philosophers call auxiliary hypotheses. What that means is that when we test a hypothesis, we're not just testing the specific hypothesis, that is to say whether the Earth or the Sun is the center of the solar system, but also various other assumptions that are built into that test. And we're also testing the reliability and the sensitivity of our instruments. So if we go back to the problem of Copernicus versus Ptolemy, the Copernican theory said the sun was the center of what we would now call the solar system, and the Earth and all the planets were moving around the sun. So one consequence of that idea was that if the Earth were moving, we should be able to detect effects. And so one of those effects that astronomers recognized was stellar parallax, the change in the apparent position of stars as the Earth moves through its orbit. So imagine a very bright star that you see in December. If you look at that star, you will see it against a backdrop, this backdrop of stars, but come June, when the Earth has moved to a different position, you're now looking at that same star from a different angle, from a different perspective, and you see it against a different backdrop of stars. That angular difference is known as the stellar parallax. So astronomers looked, and they found nothing. So according to the hypothetical deductive model, astronomers should have rejected Copernicus and stuck with Ptolemy. Well, obviously there's something wrong with that picture. So what went wrong here? Well, today we would say that the picture should look something more like this. Put another way, we would say that these scientists involved at the time were making an auxiliary hypothesis. They were assuming that the Earth's orbit was large compared to the distance to the stars, and therefore that the stellar parallax would be large. Today we would say no, that the Earth's orbit is very, very tiny compared to the distance to the stars, and therefore that in fact the stellar parallax is very, very, very small and very hard to measure. And that, of course, leads to a second point, which was that they also had a second auxiliary hypothesis. They were assuming that their telescopes were sensitive enough to detect the effect. In fact, it wasn't until the 19th century in the work of Sir William Herschel that telescopes were, in fact, able to detect the stellar parallax. So we might say that the hypothetical deductive model is an oversimplified picture of the scientific method. And in some ways that would be fair. What we see in this example is that it's more complicated than a simple hypothesis consequence model, a sort of if P then Q. But the problem goes deeper than that as well, because a good deal of science simply doesn't follow the hypothetical deductive model. A good deal of science is inductive. Induction is the process of generalizing from observations. We go out into the world, we see things, we collect information, we collect data, we do surveys, and from that information, we draw a general conclusion about the natural world. Some of the most important work in the history of science was inductive. The most famous example of that being the work of Charles Darwin. Biographers and others who have studied Darwin have shown conclusively that when Darwin went on the voyage of the Beagle, he was not testing a hypothesis about evolution. In fact, he wasn't testing any hypothesis at all. He didn't really know what he believed about the natural world. He just knew that he was interested in it, and he didn't want to be a doctor. Now, in addition to inductive and deductive science, scientists also participate in modeling. So what is that? Well, modeling is the attempt to reproduce some part of the natural world in order to try to better understand what could have caused it. Until the 20th century, there was a fairly robust tradition of building physical models to try to understand things that couldn't be experimented on in a laboratory and that could be observed in the natural world, but you couldn't see the causes because they were too far away in time or in space. And one example of this had to do with a major question in the late 19th century, the cause of mountains. Geologists in the late 19th century were very interested to try to explain how mountains formed, but since they had formed in the distant geological past, there was no way to observe it directly. And because the processes were too big and too complicated, there was no way to build an experiment in the laboratory. So scientists built models. And this is an example of a physical model in which a scientist here, Henry Cadell, is trying to account for the fact that in mountains, you often see large folds in which the rocks appear to have been folded over on themselves. These were called naps. And often the materials seem to have behaved in a very soft manner, as if they were made of clay, rather than being hard like rocks as we normally think of them. Cadell hypothesized that these features could be explained if the mountains were compressed from the side and if the rocks behaved in a plastic manner because they were hot very deep within the earth. And this became an important argument or foundation for later arguments about the theory of continental drift. Now, nowadays, most scientists don't build physical models out of clay and sand. When we talk about models today, we're usually talking about numerical simulation models, that is to say, computer models, in which we use mathematics to try to reproduce observed phenomenon. This is an early example of a computer model of global climate change. The solid lines shown here in black are the actual observations of temperature records around the globe. So this is what has really happened to the temperature of the Earth. So here's temperature, here's from 1900 to 1990, and you see that there has been this steady increase in temperature with a particularly strong increase since about the 1980s. So what combination of factors could cause this observed change? Well, scientists know that there are many things that can affect the climate: variations in solar radiation, volcanic dust, sulfate particles from air pollution. So this model takes these various causes, see how they have fluctuated through the course of the century, and see what combination can produce a model that most closely matches the actual facts in nature. And the answer is all of the above. We only reproduce the observed effect when we take into account all of these different factors. But the key thing in this model is that the only one that explains this big increase in recent decades is the warming effect of greenhouse gases. All the others either have cooling effects like sulfate, or they kind of go up and down like solar variation. They don't explain the rise in recent decades. So to sum this up, there are many different scientific methods, and at different times, in different places, and in different fields of study, scientists have preferred different methods. This led the philosopher of science, Paul Feyerabend, to say that the method of science was anything goes. Well, that's often quoted out of context. The full quotation is, if you press me to say what the method of science is, the scientific method, I would have to say that the only principle that does not inhibit progress is anything goes. In other words, Feyerabend was emphasizing that scientists are creative, they're innovative, they try lots of different things to see what works. And the methods that have been passed down through the ages are the methods that have stood the test of time, that scientists find work to answer questions about the natural world. Different scientific problems may call for different scientific solutions. So this then raises another question. Do these diverse methods have anything in common? And what I argue in the book is that the answer to that question is yes, and it's evidence. That all of these methods are means of collecting, creating, and generating scientific evidence. Evidence that helps us to develop ideas about the natural world and to see how well those ideas stand up in practice. So I argue in the book that philosophers have focused too much on method and not enough on evidence, how we judge evidence, how we evaluate it, and how we decide when we have enough to say that something is known. So evidence, I argue, is the key element in scientific knowledge, not method. But this, of course, raises another question. Who judges the evidence, and how do they judge it? Well, the short answer to who judges the evidence is scientists. Scientists judge scientific evidence. But how do they decide when they have enough evidence to say that something is known? And this is where the category of consensus becomes important. I've written a lot about scientific consensus, and I've encountered critics who say, oh, science isn't about consensus, that's just groupthink. But actually, science is about consensus, because consensus is the marker of scientific agreement. When scientists have evaluated evidence, when they've argued about it, when they've fought about it, when they've gone back to the drawing board and tried to get more data or make their studies bigger, eventually they may come to agreement. They may not, in which case they keep doing more work, but they may come to agreement. And when they do, that agreement is what we call consensus. So consensus is a marker that scientists have judged the evidence to be sufficient. Put another way, we can say that scientific knowledge is the body of claims that have been agreed upon by experts. Claims that experts have concluded are supported by sufficient evidence to say that they are true. Claims about which experts have come to consensus. Now, this conclusion troubles some people because it may appear to be an appeal to authority. And in some ways it is, but it's a particular kind of authority. It's not the authority of the individual, no matter how brilliant or wise that individual might be. It's the collective authority of diverse evidence who have weighed and judged the available evidence. And if you look at this picture, what are these people doing? Well, the woman in the white lab coat is showing her colleagues evidence. She's pointing to a picture or a graph or a chart, and they're smiling, so that seems to imply that they agree. Although I have to say, I've always been a little suspicious that this picture is actually scientists because they do seem far too happy. So what I argue in the book is that science, and here I'm relying on the work of feminist philosophers of science like Helen Longino and Sandra Harding, who have really emphasized this point in their earlier work. Science relies on the collective scrutiny of claims. We are all poor at identifying our own mistakes. Cognitive science shows us that. But we're actually very good at identifying other people's mistakes. And science capitalizes on this cognitive reality. It takes advantage of this reality and it uses it to correct error. So when we talk about science being self-correcting, this is what we're really talking about. It's not that science itself in some abstract way can correct itself. I mean, science in that sense doesn't actually exist. But it's that scientists, people, working together, presenting their findings at conferences, publishing them in peer-reviewed journals, subjecting those claims to critical scrutiny, allowing colleagues to say, but wait a second, I think your sample size is too small. Or wait a minute, I think your statistics are not right. That is the process by which scientists correct each other and eventually hopefully converge on robust claims that tend to withstand further scrutiny. Helen Longino has called this transformative interrogation. It's interrogation because it's tough. Any of us who have done science know it really can be hard. It's not always fun. Peer review can be mean, and it hurts when people criticize us. But if we understand that we're part of a larger process, we can accept that criticism, not take it personally and say, okay, I get it, I see your point, and let me see if I can address it. And it's transformative because what survives is typically not the same as what it was at the starting point. The sociologist of science Ludwig Fleck made this point back in the 1930s, almost 100 years ago. Scientists adjust their claims in light of critical scrutiny. Sometimes they go back and collect more data. Sometimes they conclude that the original idea was no good, and they try to develop alternative hypotheses and theories. To the extent that scientific knowledge is reliable or trustworthy, it is because it has withstood this thorough process of critical scrutiny. And to the extent that it's objective, it is because it has survived this intersubjective analysis. It's not just my personal view, it's a view that has stood up to the criticism of others. So again, to quote Longino, she says, the objectivity of individuals in this scheme consists in their participation in the collective give and take of critical discussion and not in some special relation of detachment or hard-headedness that they may bear to their observations. Thus understood, objectivity is dependent upon the depth and scope of the transformative interrogation that occurs in any given scientific community. And this is an extremely important point because critics of science will sometimes like to single out a person and say, oh, he's not objective because X, Y, and Z. He has a financial stake in this. Or Oreskes is not objective because she's a member of, the Sierra Club. But the point here is to show that science doesn't depend upon the objectivity of an individual. After all, the reality is that no individual can ever be perfectly objective, but it achieves objectivity through this intersubjective analysis. So to sum up then, what we call scientific facts are claims that have withstood this critical expert scrutiny. And this then brings me to one more point, which is the importance, the essential aspect of diversity in science. The processes of transformative interrogation are most likely to work well when a scientific community looks at a problem from a variety of angles. And that is more likely to occur when the community is diverse than when it is homogeneous. So let me talk a little bit more, we have a few minutes still, about diversity and its relation to this question of objectivity. To understand why diversity is crucial for the success of science, we have to think again about objectivity. So many people, perhaps most people, think that science works because scientists are objective. And certainly it's true that all good scientists try to be objective. We can say that objectivity is what philosophers call a regulative ideal, something we try to live up to. Most people think of objectivity as a characteristic that inheres in individuals. So sentences like, I am objective, she is not objective, a good scientist is objective, these sentences seem to make sense. They're sentences that we can understand. But the reality is that various scholars, cognitive scientists, linguists, philosophers, have said, well, actually not so fast. Because the opposite of objectivity isn't bias, it's subjectivity. And we are all subjective, because all perception is subjective. So think of it this way. It's conventional to compare objective facts with subjective opinions. So on the left, an objective fact, The Force Awakens is the highest grossing Star Wars movie. On the right, a subjective opinion, The Empire Strikes Back is the best Star Wars movie. So we're all familiar with this kind of a distinction. Or over here, these are oranges, an objective fact. I love oranges, a subjective statement. But it doesn't actually solve the problem, because one of the things we know from cognitive science is that different people can look at the exact same objective reality and see different things, interpret different things, have different perceptions of what it is they're seeing. And I should just go back for a moment. And it's not that any of these are bad people. It's not that they've necessarily been corrupted or that they're racist. They simply, because of their prior expectations, have different thoughts and ideas. They see different things when they look at the same stimulus. Or look at this one. This seems pretty obvious. Those are oranges. I love oranges. But actually, are we sure they're oranges, not tangerines or clementines? Or maybe they're actually plastic fruit. We need to do more work to find out if they're actually oranges. Or how about this one? Is it a 6 or is it a 9? The reality is that people see things in different ways. It's not a matter of objectivity versus subjectivity or bias, because on some level we are all subjective. We see things from our own preferences, and we evaluate them according to our experience, our values, our habits, etc. This doesn't make us bad people or even bad scientists. It just makes us human. Think about this classic example of the 6 blindfolded people and the elephant. Each correctly perceives a portion of the creature. Each correctly feels or observes something, But because their perspectives are incomplete, they don't have an accurate picture of the elephant. So let's apply this to science. Imagine a scientific community that is homogeneous. It will tend to look at things in the same way, and therefore it's more likely than a heterogeneous community to miss aspects of a problem that might in fact turn out to be important. Many past errors in science in hindsight can be explained in this way. And in the second half of the book, I give some specific examples of cases where we would say in hindsight that scientists didn't get things right and that the science was not trustworthy. And in most of those examples, we can see that the communities were not diverse and that they had significant blind spots that are obvious to us today because we are more diverse, because we are women, because we are people of color, or simply because the world has changed. Or we can see in some cases there was significant informed dissent, but it was brushed aside. Now, this has very important consequences. And so I conclude towards the end of the book that we shouldn't trust the opinion of just one person. If an individual is standing up in public and making strong claims, we should ask, does that individual actually represent the consensus of a scientific community, or is he just offering us his opinion? Similarly, we should not jump to conclusions based on a single study. And we see the mass media do this all the time. A new study comes out and they rush to say, oh my God, look at this new study. And then a few months later, we find it doesn't hold up. And people say, oh, see, we can't trust science. But no, we can trust science. But what we can't trust are single studies or the opinions of single individuals. Science is a collective project, and collecting and evaluating evidence takes time. If the community making a claim is very homogeneous, we may be warranted in looking for a second opinion from other qualified experts. So, to conclude then, why should we trust science? Well, mainly because of its track record. This is an enterprise with a long track record of success in explaining the natural world, curing diseases, supporting technological innovation. And that track record can be attributed not to a single scientific method, but to the shared processes of critical scrutiny of evidence, which over time may lead to scientific agreement, which we conventionally call consensus. Scientific knowledge is not based on genius, it's based on many people working together. And it works because of the accumulated experience and expertise, and that works best when a diversity of perspectives have been brought to bear on the question at hand. Put another way, we should not trust scientists as individuals, but we do have good reason to have confidence in the process of which they are a part. And there's one more consideration. If we return to the question of Pascal and the type 1 and type 2 error, we can ask ourselves the question, well, what are the consequences of accepting scientific evidence if it turns out the scientists are wrong, versus the consequence of rejecting that evidence and it turns out the scientists are right? When it comes to climate change, the issue I have worked on most closely for the last 20 years, if our scientists are right and we ignore their findings, the consequences are almost certain to be quite dire. But if, on the other hand, we accept climate science and it turns out the scientists weren't really right, well, then we will have created a better world for nothing. Thank you very much.
I really love that final picture. I said it's so compelling, and thank you very much for your talk. I think it's magnificent to have this kind of conversations. And let me mention that how I came to know Naomi is because I read her book, and I became so excited about it that I actually contacted a mutual friend of ours and said to her that we should translate this to Spanish, because what you said and the way you said it was very compelling, simple, and profound, and at the same time engaging, because it talks too much to examples. It's not just ideas. You know, it's really a human book. You know, it's a way of humanizing scientists, which many scientists may not like, actually. you know, because as you point out in the book, I mean, there's all these issues about trying to behave like we are, that we are objective, that we don't have values, that values are not involved in our decisions or in the way we write. And it is the complete opposite. I mean, we are human beings. And as you said in this part of the book, which I really love it, is say, would you trust someone who actually don't have values? No, because you have to be a human being. So I want to ask you a couple of questions and comments. And one of these questions I want to start with is about yourself. I mean, because you are a scientist, you were trained as a scientist in geology, and then you moved through and became a philosopher, a historian of philosophy, and a story of science, and that's an interesting path, you know. And I'm asking you this because it looks like most scientists don't reflect too much about the philosophical questions, and I think that's part of the problem. So, if you can comment a little bit on that, in terms of your personal life too, and how philosophy actually might have made a difference in your career.
Mm-hmm. Thanks. Sure. Well, thanks for the kind words about the book, and I'm glad that it's human. I just want to say I do think that this issue about how scientists present themselves is very important. I think a lot of scientists are raised with the idea that we're not supposed to show the human dimension of our work, or especially the human dimension of ourselves as people. As Longino says, we're supposed to be hard-headed, we're supposed to be detached, we're supposed to be unemotional. And of course, this was used for centuries to argue why women could not be scientists, because women were obviously too emotional to be scientists. And so partly I was interested in this because of the gender component, because of the way arguments about objectivity had been used against women, and also people of color and others as well. So what I came to initially was to say, no, that's wrong because it's used to exclude people. But now I've evolved to say, well, it's even worse than that. It's not only that you exclude talented people, but you actually present a false image of what this project is, a false image that then subjects you to criticism when you make an error. Because we see this in a lot of climate change denial and other criticisms of science. Scientists make a mistake, and if the mistake becomes public, people say, oh my God, look, they made a mistake. And so they're sort of taken off their pedestal, or the gods have been shown to have feet of clay, and then this is used against science. Well, scientists have set themselves up for a fall. If you make a claim that is clearly false, it's only a matter of time before people will begin to realize that it's false. But if, on the other hand, you say, well, of course we're human, we're people, science is a human enterprise, just like music or art or business, and people make mistakes, there's no such thing as an infallible human being, then when you make a mistake, you say, oh, yeah, wow, we made a mistake. And then you actually show the strength of science. And I've thought about this a lot, because I think at the end of the day, the thing I love most about science is the capacity of great scientists to say, oh, yeah, I was wrong about that. And so in my book on plate tectonics, the book begins with an anecdote, which I still treasure. I mean, the book was written quite a few years ago now, but a very, very famous scientist told me the story of how in the 1960s, he was working on his PhD thesis at Columbia University, at one of the centers for geophysical research in the world. And he had just finished his PhD thesis showing how the heat flow data proved that plate tectonics could not be true. So now imagine this. You've just finished years of work. You've submitted your PhD dissertation. You've passed your examinations. And then he went to a conference and he heard some presentations on the new theory. And he said, and this is the story he told me, he went home and he said to his wife, pour me a stiff drink. Everything in my dissertation is wrong. And then when he had sobered up, he went back to work, he embraced the new theory, and he wrote a paper that became one of the most highly cited papers ever in the history of science. And that to me is just a beautiful example of how a scientist embracing this idea of openness to learning can use that to advantage. So if you're interested in that, my book on plate tectonics, that story is in that book. And I love that story. Me personally, Yeah, so my own personal story, well, it's kind of complicated. I was always interested in history, philosophy, literature. It was hard for me to decide what to study in university because I had too many different interests, and people told me that these interests did not go together and that I had to choose one or the other. So I chose geology because it was fun, because I could be outdoors, and because you could get a job. And I didn't know you could get a job as a historian of science. And in later years, when I discovered that you actually could get a job as a historian of science, that was, really important for me. But I want to tell one other story because it's very relevant to this conference. So some of you may know that I worked in Chile early in my career in the early 1990s. I did a research project at El Laco, the large ore deposit, the iron ore deposit. Well, it's not actually large. It's scientifically significant, but it's not large. And I just want to shout out to Jaime Arias, who helped us do the logistics for that project. This is now going back 30 years ago. Part of the reason I was interested in that ore deposit was because there was only one study that had ever been published on it. Well, then there were a couple more, but there was one very famous study that I had read in college, and it just didn't seem right to me. Some of the claims seemed odd, surprising, and it was a very short paper. It didn't have a lot of data. And so I just thought, I feel like there's more to be said here. Now, as it happened, the person who had written that paper, a famous American geologist, by that time retired Stanford professor Charles Park, was still around the university when I was at Stanford as a PhD student. So I went to see him and I said, Professor Park, I'm kind of curious about this paper you wrote because it doesn't have a lot of data in it. And, everyone accepts it. Everyone says, oh, El Laca is a lava flow because you wrote this paper. And he says to me, oh, that paper? He goes, yeah, we were only there about 2 hours. We had very little time to collect samples or really look closely. I wish someone would do some more work on it. And so we did. And in subsequent years, other geologists, including a number of Chilean geologists, also worked on it. We now know that it's a complex hydrothermal system that is part of a much larger group of ore deposits that have now been pretty well studied around the globe, some of which are very, very significant economically. But lots of people had made assumptions about this deposit based on one study, and it wasn't even a very good one. So that was an early lesson in my life about not trusting single studies and understanding that the path to scientific knowledge is a collective one, and that it takes time to sort out these complicated, the natural world is complicated. It's difficult. The reason we have science is because the answers are not obvious, and it takes time to get to those answers.
Yeah, definitely. And that brings the other question that most of the problems we face as society, as a civilization, and also as a biosphere these days are related to very complex processes, are very complex in themselves, and they are not match for our kind of single-minded, narrow way of actually studying the world. So there is a mismatch in terms of the complexity of the processes and the way we are studying them. It looks like the elephant parallel is becoming more and more evident, and we need to do something in order to, so to speak, to improve this collective, because we have to act now. We have to do things, and especially with climate change. So what can we do? How can we foster this more transdisciplinary way of thinking to deal with these complex problems?
That's a great question. And I think that we've seen universities have become much more open to transdisciplinary and multidisciplinary research in recent years. I see in my own students that they are much less afraid to try to do interdisciplinary work. And we see universities that have tried harder to figure out ways to evaluate it. But we still have tenure and promotion systems that are really based on very old-fashioned notions of disciplinary evaluation, right? Historians get evaluated by other historians, biologists by other biologists, rather than other people who look at the same problem, even though they may look at it from a different perspective. So I'd like to see universities continue to embrace a more interdisciplinary perspective so that when we evaluate people for promotion and tenure, we would do it not so much from the standpoint of the discipline, but from the standpoint of the problem. So if a person works on global poverty, for example, it wouldn't really matter whether they're a sociologist or an economist. We would get other people who work on poverty to look at their work. And the same with climate change. You know, climate change is interesting because it really isn't one thing. I mean, we call it climate change, but why do we care about climate change? Because of all the different ways that it can hurt people adversely by making hurricanes worse, or by changing the conditions for agriculture, or by sea level rise that can displace people. And so to understand all these different dimensions, you can't just have atmospheric physicists, right? And the IPCC recognizes this. And if you look particularly at the most recent IPCC reports, they're very impressive in the range of disciplines that are now engaged. But that took a lot of time to get there. And so I think we need to continue to do that. Just to say one more thing on that, if you think about the disciplines that are in most universities, history, classics, languages, physics, biology, I mean, these disciplines were developed in the late 18th and 19th centuries, right? These categories of knowledge are now very old. We now live in the 21st century, and the world doesn't give us problems in general, the big problems of the world, as you suggest, problems of poverty, of inequality, of climate change, of environmental damage. You know, these are not given to us as problems in biology or problems in physics or problems in history. They just come as problems. And if we're going to solve them, we have to break through, in a way, the shackles of disciplinary thinking.
Yeah, there's this famous saying, and everything I can, I say, because I think it's important. There's this saying, I don't remember this, I think it was a Nobel Prize at some point that said that the world has problems and universities departments, you know?
Exactly.
So it's like,
exactly.
it's nonsensical. But thank you very much for your comments. So I want to look a little bit about the big picture here in terms of the way philosophy has been moving these last decades, at least for me, my reading, which is, I'm not an expert, but I'm usually interested in this kind of issues, is it looks like there is a continuous movement of realizing that we need to be more humble. And you said it in your book, and not only because we are human beings and that's the only thing we share, nothing else, and we are all equal in that sense, but also because the human condition is such that everything that we do is sort of incomplete, you know, in terms of there is a impossibility of actually grasping the whole reality, you know, and this impossibility, and you mentioned the word incomplete, and I want to connect that with the incompleteness theorems that were put forward back in the 30s, when Turing, Church, and also Gödel showed that science was incomplete by showing that there are things that you cannot decide if they are true or false. So it looks like we never learned that lesson, so that we just look the other side and we want to keep the illusion of rationalism, of humans being rational and different from the rest of the nature. And it's weird. Can you comment a little bit on that?
Yeah, I can. Sorry, I just,
No
sorry, yeah. I have to turn off the phone here. Yeah, I think that's a really great point, and it's something that we should talk much more about. And you're absolutely right. So if you think about the philosophers of the 1920s and 30s, all of the work that was done on underdetermination, Heisenberg's uncertainty principle, as you say, Gödel's incompleteness theorem, philosophers recognize, and mathematicians and scientists, that the idea of absolute knowledge could not be fulfilled. And it wasn't just that we were fallible as people, it was that no matter how smart we were, there will always be these aspects of problems that were inaccessible to us, or mathematical problems that were underdetermined because there was more than one solution to the problem. And there is a way in which it's almost as if we as intellectuals and academics refuse to accept that. And so you still find many people, including many scientists, arguing for a vision of, you know, what I call positive knowledge, right? The Comtean vision of positive knowledge, that somehow, if we just work hard enough, we will definitely find out for sure, absolutely positively. And you see this in a lot of scientists who still say things to imply that, that our knowledge is right and absolute and correct. And I often wonder why they do that, because it doesn't actually make any sense. It sets them up for failure, as I've already said. You're making a claim that you cannot actually sustain. So you're opening yourself up to vulnerability when error occurs. And I don't really know what the answer to that, except I think it's a kind of deep cosmic insecurity, that accepting that what we do is provisional, that it's a learning process, requires us to be humble, and it requires us to be respectful of colleagues, especially colleagues in other disciplines who may have important perspectives to bring to the table. And I think that for scientists, especially really famous scientists, the sort of scientists who get to comment on television, they're used to being the big man on campus. I don't know if you have that expression in Spanish, but they're used to being the big man, the center of attention, the expert to whom journalists look for answers. And I think a lot of them enjoy that position. And so it's a kind of ego problem, right? That in a way, to really be successful, I mean, it's kind of like the argument from Zen Buddhism in Zen mind, beginner's mind. The beginner's mind has many possibilities. The expert's mind has only a few. If you fashion yourself as an expert and you begin to connect your sense of self-worth to your role as an expert, it can be hard to admit when you don't know the answer to something. But the only way to learn new things is to accept that you don't know everything. And so I guess it's kind of a call for scientists to let go of the ego piece a little bit. And I know that's hard to do, especially if you're very brilliant and very successful, and all your life people have been telling you how fantastic you are. But even the smartest people make mistakes, and even the most knowledgeable people still have more things to learn.
Indeed. There's sort of a pandemic of narcissism in science, I think. And it's like we become ill of over-existing. I mean, it's like you want to exist. Come on, I mean, it's easier if you are humble and you just try to be happy. But sometimes it's very difficult because we are embedded in a society which actually put a lot of carrots, on people actually, being famous. And fame also comes along with money, power, influence. So there is a synergy of it's like climate change. It's a synergy of many causes that can get you very ill sometimes. But that aside, one of the things I love about your book also, for me, was a complete discovery of many philosophers, and especially women philosophers that were completely kind of invisibilized for so many time. I mean, for such a long time that now I say, how it comes that I never heard of Helen Longino or Sarah Harding. I've read a little bit of Hathaway, but Longino and Harding, they blew my mind. I mean, it's just like, what clever, way of saying things, and provocative. I mean, as you said, Sarah Harding said that Newton's Principia was a rape manual, a manual for rape. So it's like, wow, these women are like fighters. And they said this back in the 60s and 70s. So what is your kind of a reflection on this invisibility of a woman especially in philosophy?
Mm-hmm. Yeah, well, thank you for that, because it is an important part of the book. And one of the things I really tried hard to do in the book was to point out that the arguments I was making were not original to me, that many people have been trying to bring this idea forward over the last decades, especially in the 80s and 90s. I mean, many of these ideas were coming to the fore when I was in graduate school or I was an assistant professor. And so part of what I was trying to do was to kind of give them another hearing and integrate them into an argument about science that wouldn't necessarily just be viewed as a feminist argument. So I think two things happened there. And both Sandra Harding and Helen Longino have had good careers, so it's not like they've had no attention to their work. But I think that it's very easy for male philosophers to ghettoize that work and call it feminist philosophy of science, when we really should call it philosophy of science. They are trying to understand how science works. What does it mean to say that something is objective? Is it even possible for science to be objective? And so those are core central questions in philosophy of science. And that's so part of what I was trying to do in the book. And this is an argument that Helen Longino herself has made many times, is to integrate this into a longer history of people trying to think about what science is as an enterprise. And so in the book, I situate them in this longer discussion. Now, you're absolutely right, though. They have been made invisible, disappeared by many men. And I think that this is the sad reality of the world we live in, that despite the many advances that women have made in academic life, there is still a tendency for men to cite other men, to invite other men to be the experts. And so I'm very glad that you've invited me here today.
Thank you.
There's a kind of, for journalists, if you look at who are the scientific experts on television, mostly men, even though there are lots of women who could be invited. One time I did a little non-scientific experiment. For a month, I counted when there were opinion pieces in the New York Times dealing with science or technology, I counted how many of them were written by women versus men. And the answer was there were no pieces, 0 pieces on science and technology unless they had to do with women's health. So, women's medicine. Now, again, I think that's changed a bit. I've written for the New York Times now. But this sort of assumption persists that scientific experts are mostly men. And it's a kind of laziness, right? We all tend to be influenced by people who are like us. So men tend to reach out to other men. And there's lots of literature on this that shows it doesn't mean that they're consciously sexist, but there's a kind of implicit bias that operates. And there's all kinds of other ways that it works too. Like studies have shown that radio was optimized for men's voices, not women's voices, which is why women can often sound shrill on the radio. So, these things play out on so many different levels, and it's important for us to be aware of them and to think about that and to make sure that we don't unconsciously recapitulate those faulty assumptions.
Yeah, we all have a responsibility to our collective, and I think that that's a wonderful point. And I have more questions, but I would like to honor the collective here and see if anyone has a question. Well, there are microphones. There is a question over there. There are 2 questions. Can we have a microphone, please? Can you raise your hand again? There you go.
Perdón, por el tiempo me indicaron que no se podían realizar preguntas.
Okay.
I'm so sorry.
They say that we are over time. So
okay.
there is not going to be any question, but please feel free to actually send the question directly to her through the email. And just want to thank you again for your talk and being here.
Thank you.
And
it's been a pleasure.
for writing this wonderful book for the collective. So thank you very much. Yeah, we will be a little bit better if we read your book, I think. Thank you. A pleasure.
Okay.
Bye.
Buenas tardes.
Buenas tardes. Bye-bye.
Bye.